To understand how AI works, we have to look at how computers used to be programmed. For decades, software ran on simple, rigid logic. Think of a standard household thermostat. You give it a strict rule. If the room temperature drops below 67 degrees, then turn on the heat. That straightforward if-then logic is perfectly fine for machines operating in closed systems. But the moment you force a computer to process something as messy and unpredictable as human language, that rigid framework shatters. The earliest battleground for this was the email inbox, specifically the fight against spam. Look at this diagram of a standard rules-based filter. If an engineer writes a line of code instructing the system to block any message containing the word Viagra, a spammer can bypass that barrier instantly. They just swap a single letter for a number or add periods between the characters. The computer, blindly following its exact instructions, lets the junk mail slide right through. Programmers realized they could never manually write enough rules to anticipate every possible typo or trick. Instead, they had to build a system that could look at thousands of examples of junk mail and figure out the underlying patterns on its own. This is the core concept of machine learning. You don't give the computer instructions, you give it data. Decoding human communication requires a machine that can adapt to context, marking a hard limit to what strict if-then commands can achieve. To teach a machine to identify spam, engineers use a method called supervised learning. They start by feeding the model a massive dataset of emails that human reviewers have already explicitly labeled as either spam or not spam. This human-provided label acts as the absolute truth for the computer. But a computer can't actually read English. To process the text, it has to convert the email's characteristics, like the length of the document or the frequency of certain words, into numbers. What we see in this diagram is a multidimensional scatter plot, showing how the algorithm translates an email's vocabulary into specific mathematical coordinates. As the model looks at the training data, it makes it guess on whether an email is junk. If it gets it wrong, a mathematical function called a loss function calculates the exact size of the error. The algorithm then slightly shifts its internal parameters to reduce that error on the next attempt. Notice how the data points reorganize as the machine slowly isolates the spam cluster from the normal messages. After millions of these microscopic mathematical adjustments, the model zeroes in on the optimal configuration. When a brand new, completely unseen email arrives, the system can instantly map its coordinates and accurately classify it. The system hasn't learned to read. It has simply drawn a highly precise mathematical boundary around the probability of a threat. Sorting junk mail is a binary choice, but humans communicate with deep, messy subjectivity. To analyze emotion at scale, say a company parsing thousands of customer reviews on their digital storefronts, engineers employ natural language processing to perform sentiment analysis. The first step in this process is called tokenization. The algorithm takes a full customer review, strips out filler words like the or and fractures the sentence into raw, isolated tokens. Using statistical formulas, the model weights how often specific words appear across the entire batch of reviews. It mathematically maps the relationship between positive terms, like excellent, and negative ones, like broken, plotting the overall emotional intent of the text. By doing this, corporations can take the highly subjective nature of human frustration or joy and compress it into neat, calculable data points. Analyzing language is one thing, but producing original prose requires a totally different architecture. This technology powers the autocomplete features on your phone and the smart speaker on your kitchen counter, moving AI from passive reader to active conversationalist. Early text generation models struggled because they processed words sequentially, one after another. By the time the computer reached the end of a long paragraph, it had essentially forgotten the subject introduced in the very first sentence. That barrier was broken by the transformer architecture and its attention mechanism. Look at how these lines connect a single pronoun to earlier nouns in this diagram. Instead of reading word by word, a transformer looks at the entire sequence simultaneously. It calculates the mathematical importance, or attention, that every single word demands from every other word in the text, preserving the full context instantly. Fascinated to train these massive networks, engineers use self-supervised learning. They take vast databases of text, like the entirety of Wikipedia, mask certain words, and force the algorithm to guess the blanks. Over billions of cycles, the model isn't just predicting the next token. It internalizes the complex structural relationships and logical flows buried in human records. By mastering these sequence probabilities across the entire internet, the machine eventually gains the ability to simulate high-level debate or write poetry. It produces human-equivalent fluency because it has mapped the exact statistical path a human mind would likely take through any given sentence. A modern language model can debate the nuances of existentialism with absolute fluency while possessing zero actual cognitive comprehension of a single word it speaks. Researchers often refer to them as stochastic parrots. Because they are trained by indiscriminately scraping massive, uncurated swaths of the internet, they absorb all of our underlying biases. If the training data contains racist rhetoric or toxic behavioral patterns, the algorithm will faithfully replicate and amplify those flaws, treating them as valid statistical probabilities. And when these models make a mistake, we cannot easily fix them because of the black box problem. The deep neural networks running inside server banks like these are so densely layered with billions of parameters that even the engineers who built them cannot trace the exact mathematical path the AI took to reach a specific output. This combination of absolute fluency and absolute opacity is incredibly disorienting. During the testing of Google's Lambda chatbot, the conversational responses were so contextually perfect and emotionally persuasive that an experienced evaluating engineer became convinced the software had developed genuine feelings. These models function as sophisticated statistical mirrors, reflecting the brilliance and the deep-seated flaws of the human data used to build them.